All right, everyone, welcome to week 2. So today, sharp, which is cool. So I'm not sure we need it today. Have it. We're going to talk about thermodynamics. And I realize this stuff's a little bit dry. I apologize about that. But again, I kind of want to just make sure we're on the same page because the text uses a lot of this stuff to just explain various principles and properties of materials. So I felt like it was useful to spend a little bit of time just, kind of reviewing things a little bit. Just going to check really quickly to make sure that the view is correct here. So this is in chapter 2 and 3 of the book. And I realize there's a lot of reading here crammed together, but I'm also kind of assuming some of this stuff is review. And don't worry, the pace will definitely slow down with the reading. It's just how White has divided stuff up. But today and next time, we're talking a little bit about thermodynamics, and particularly from the perspective of chemical equilibrium. And so there's some stuff to talk about here. Phase rule, enthalpy, entropy, Gibbs function, equilibrium constants, and then we'll start to talk about mixtures of materials, and then we'll talk about something called chemical potential. And this might be the only thing on the list that you haven't perhaps been introduced to before, but then next time we'll use that to talk in a lot more detail about mixtures, and especially mixtures with non-ideal materials. So that's kind of where we're headed this week. And like I say, it's kind of spread out in chapter 2 and 3. He uses a pretty kind of strict way of, calculus-based way of defining stuff. If you have any questions as you're reading it, shoot me a message, no problem. I'll be more than happy to, chat with you about it. So just to remind you about a little bit of stuff, when we talk about thermodynamics, we usually define something called a system, which is the area that we're focused on physically in space that we know something about, like its temperature and its pressure, and we know something about the chemical composition there, and however many components there might be in there, and we can quantify them. So in some ways, it's like a reservoir, like we talked about before last week in geochemistry, but the difference is that this is much more rigorously defined and usually smaller. Okay, so these are just what some of those terms actually mean, right? System is a collection of matter in an identifiable place. Component is something that can be used to describe chemical variation within a system. So the components are usually individual, unique chemicals, and these are distinguished from phases, which are the physical form of a chemical, right? So like if you've got a system with some various forms of water, you've got ice, maybe you got some water vapor, you got some liquid water, that's still just one chemical component, but it's 3 different phases, right? So we would define that. If we had a system that just had water in it, it would have just one chemical component, but it would have, like I said, 3 phases. Another example would be if you had the chemical SiO2, it could be found in the mineral core, or found as chert, it could be as cristobalite. Again, one chemical, 3 different phases. Does that make sense to everyone? Not just unclear. Okay, so components are used to kind of describe a system. We're looking for the maximum amount of information about a system that allows us to define what its state is, whether or not it's going to react or not react or whatever, on the basis of the maximum number of observables, of which most of them are chemical components. Okay, and the other aspect are the phases. So the other thing to remind yourself about is like, what does a system mean? These are just some simple infographics I found on the web. And think by analogy to reservoirs, which we talked about before, physically definable places on Earth. And in a chemistry lab, the system might be a beaker or a flask, as is shown here, with the system being defined as inside that flask and the surrounding, which we talk about a lot in thermodynamics, is exchanges or lack thereof between the system and the surrounding. And there's a boundary, which is obviously the wall between them. And there's these three kinds of systems. Ones that are considered open, which are really common in the earth sciences when we talk about these a lot. These are ones where the system can exchange both heat and mass with the surroundings. And just think about, for instance, a mantle plume rising up through the mantle to eventually, reach its point of decompression, melting. It melts underneath, for instance, the Big Island of Hawaii, and then magmas bleed off of it. That parcel of mantle has been exchanging heat with the surrounding mantle, and then when it starts to melt and release magma that buoyantly rises to the surface, it exchanges mass as well. So that's an open system. And we use certain thermodynamic considerations for open systems that are more complicated because open systems evolve in time, especially if they move through pressure and temperature space, than closed systems. So closed systems are closed at least to mass transfer. We can use this in some settings in the earth sciences. It just depends on the conditions, but if the system is big enough and defined enough, then we can treat it as if chemicals aren't exchanging with the outside world, but there's almost always heat exchange. Okay. Sometimes you'll hear people talk about that process being adiabatic. Adiabatic is a process that happens without the exchange of heat between a system and surroundings. It's basically a conservation of heat, and that's usually restricted for isolated systems. Okay, and these almost never exist in nature, but they're useful to make calculations for because they're the easiest ones to calculate, and we can get at least a guesstimate of the conditions that we expect in a certain setting. So the system holds all the chemical components that we talked about on the last slide. And that brings up this thing called the phase rule. Phase rule is like a shorthand way of saying how much can we know about a system based on what we know about a system, which is a fancy way of saying that the degrees of freedom or the constraint on the system, and the lower this number, the more constrained the system, right? So if we get into a system where there's F equals 0, that means that there's no variables unknown. And the higher F is, like 1, 2, 3, 4, that tells us how much we need to know about that system to fully describe it. So if you have an F equals 4 situation, which is kind of common in the earth sciences, we have to gather a lot of information to understand how that system is evolving. So this phase rule F, which is the degrees of freedom, equals the chemical components minus the phases plus the number 2. And sometimes this is written with, instead of with a P, with the Greek letter phi, capital Greek phi. And so it's basically the same thing. So C are the components, and P or phi are the phases. So for instance, as we talked about, with the silica example, the minerals that are present, and these are the chemical constituents. There's 2 other things that we almost always know about a system besides the chemicals and the minerals, and that is the pressure and the temperature. Or maybe we don't. One thing we do commonly in earth sciences is look at assemblage of minerals, try and make some assessment on the basis of how homogeneous those minerals look under the microscope to decide if they were at chemical equilibrium. And if they were at chemical equilibrium, we can sometimes estimate the pressure and temperature from the chemicals that are present. That's useful in metamorphic rocks, it's useful in ore mineralogy, it's useful in petroleum industry. So for instance, this is kind of how we use the phase rule. It's just a reminder of what we need to know about a system to know stuff about a system. So this is the water phase diagram, and we got temperature, across the bottom in degrees Kelvin. And we've got pressures in bars going up here. And this is the part of the phase diagram that we're kind of familiar with, that we think about all the time, where there's steam and liquid water and solid ice. And this is like the super high pressure stuff that we mostly don't encounter, at the surface of the Earth. And we know that there's, various things that you can read off this diagram. For instance, if someone gave you a temperature and a pressure of, whatever, 500 degrees Kelvin and 1 bar, you would go over here and you say, no, okay, that's a completely vapor filled system, or something at 300 degrees and 1 bar, that would be completely liquid, right? Remember, Kelvin 273.15 is plus the degrees centigrade. It tells you what the degrees Kelvin are. So if we sat on this line, right, the boundary between liquid water and vapor, and this line comes up here and it continues along, and I've just tried to draw it kind of not so well in PowerPoint. This is basically called a univariate condition, right? And a univariate condition is something where when we apply the phase rule, F equals 1, we only need to know one thing to know everything about that system. This is because we know that we've got 2 phases, right? P equals 2. We got 1 chemical, just water, right? So we can plug that stuff into the phase rule equation, right? And when we solve for F, we come up with the number of 1. That means that if we know either temperature or pressure, we know where we are on the stuff, right? So without being told the temperature or pressure, and someone says you're on this line, you could be anywhere along this family of green points. But if someone tells you a temperature, right, 300 Kelvin, for instance, then you will know what the pressure of the system is. It's whatever that number is over there, something like 0.4 bars. Does that make sense? Yeah, I have a few more phase rule examples. They're just helpful to be able to distinguish the difference between phases and chemicals or components. The first one is putting some glucose in water. Just to remind you of the notation here, it's the chemical equilibrium, solid glucose, C6H12O6, reacting with liquid water to dissolve C6H12O6 aqueous. This is a chemical that doesn't break apart. It's covalently bonded. It goes into water. It retains its chemical form. It just gets solubilized. So what do you guys think? How many phases are present here? How many chemicals are present?
3.
Say again?
Is it 3?
3, okay. How many chemicals?
Maybe 2.
2, yeah, okay. So then the phase rule would tell us if it's whatever, 3 minus 2 plus 2. So it turns out that there's actually only 2, sorry, I don't want to trip over this one today, 2 phases. It's a little bit of a trick.
Oh,
This is the aqueous phase. So these 2 things are together as a phase. And so we've got 2 phases, we've got 2 chemicals. That means if we want to fully describe this, meaning like how much sugar is in water, how much is this way versus this way, we have to know the temperature. Here's another one. This one has got sodium chloride as a solid, water, and now sodium chloride dissociates to make sodium ions and chloride ions. So in this case, how many phases are present?
Is it 2?
2.
Yeah, okay. How many chemicals?
Is it 2? I don't
Kind of
know.
like by now to that one,
I don't know.
except this one is separated apart
Yeah.
into 2 identifiable things. So water, sodium ions, chloride ions. You're like, what? you know, these two things make up this one chemical. So because it's an ionic solid, we treat it as two separate chemicals. I know it's a little bit kind of maybe tricky to think about because of a chemical reaction going on, but the reality is that you can't get this and this without this, or if you're going in the back reaction, you can't make this without this plus this. So there's basically two actual chemicals involved in the making of this. So that's why this counts as 2 plus the water counts as 1. It counts as 3. I got one more. Does everyone familiar with the mineral olivine? Right, it's common in our rocks here. So it's got a couple of end member compositions. The pure magnesium composition, forsterite, and the pure iron composition, phalite. In most places like here in Hawaii, it'll be something like 70, maybe 80%, maybe sometimes higher of this, with the rest being that kind of mixed in. And they're perfectly miscible materials to make a solid solution. So here we've got olivine as 2 end members written out, and magma. So this is sitting in, you know, frozen lava. So what do you guys think about that one? How many phases are present? Remember, phases are like a physical, solid or liquid or vapor things.
One.
Well, so we've got
It
the
doesn't
olivine
say.
grain, that's one. What about the frozen magma? Wouldn't that be a phase? It's a solid phase. There's 2 of those.
Wait, but doesn't it say so they count as one phase, or am I just?
Yeah, so these 2 together,
Oh, okay,
dissolve together, they count as one phase.
gotcha.
But this other stuff, the melt or the
Oh.
magma or whatever that's now crystallized or solidified anyway, counts as the other phase.
We'd have 2 solids, solid and
2
solid.
solids, exactly. So there's 2 phases. So we, you know, some people might say, well, why don't you count this as 3? And the reason we don't is because they're completely mixed together, right? So there are some minerals that have mixtures like this that form at high temperature, and then when they cool, they separate. So for instance, certain forms of feldspar minerals at higher temperature, they're mixed, calcium and sodium end member, or the sodium and potassium end member. And as they cool, they unmix. And we look at them under the microscope, we see all these cool little textures because the 2 chemicals are separating as they cool down. In that case, if they were unmixed, then we would count it as multiple phases, right? But in this case, they're completely mixed, or at least I'm telling you they're completely mixed. And so we count them as one phase. The chemicals, because there are 2 identifiable chemicals there, right? We've got the phosphorite and the forsterite and the phalite. So we've got two separate chemical components. This is basically just assuming, for the sake of simplicity, that the magma is just made of the same chemical components. If we added in all the stuff that the magma is actually made of, we would need to know more. But for the perspective of the olivine crystal, there's 2 phases, there's 2 components, and so we need to know temperature and pressure to define what mixing ratio of these 2 things we would get out at a specific temperature and pressure. And it turns out that depending on the temperature and pressure, if you have the same magma composition, all of the things being equal, you can change the composition of this thing that crystallizes out of a melt just on that basis. And these are things that we'll look at in a little more detail. So that's just I realize it's difficult sometimes to get your head around some of these ways of thinking about stuff. And I don't want you to stress too much about that, but if you can always kind of try to remember when you're looking at systems to separate out the chemicals and the phases, that becomes really helpful here in the earth sciences. As you'll see in a second, we get to these situations where we can have like the whole periodic chart worth of stuff in a rock, right? And so like, oh my gosh, there could be, you know, whatever, 50 components in there. And we make a lot of simplifications, and we make simplifications on the basis of whether or not something is energetically significant to the material, right? So like if there's a lot of something present, then we'll count it as a component in the system. And if there's just like a little bit, a trace amount that partitions into that system on the basis of, some affinity to be there or not, but doesn't really affect the energy of that system, then we don't count it. And so that's the distinction between, for instance, what we call trace elements or trace constituents of materials and the major components. Usually, just because life gets too complicated, if we try to include everything, we usually only consider the major constituents. So, for instance, if we go back to that, the last magma thing, that, example, and we think about, all the other, basaltic major elements besides the three that are, listed here, which are, magnesium, silicon, and iron. There's the aluminum and the calcium and the potassium and the sodium and the phosphorus, et cetera, it becomes more components. It becomes much more complicated. There's a lot more degrees of freedom. We need to know more information to be able to solve problems in petrology. You can even have dissolved gases like water and carbon dioxide in a real magma. It starts to get really, really complicated. So that's where we get to this distinction that I was just mentioning. The major components of a system, natural, geological system, for instance, is anything that's present in significant enough concentration to substantially affect the material properties or the energy of the mixture. Okay, and this is common thinking in a lot of different settings, but will, for instance, especially use it in high temperature geochemistry when we're describing that. And trace constituents, sometimes called trace elements, can be present in small quantities that sort of don't affect the energetics or the material properties of a system. Okay, and so they don't contribute to F. They contribute in an important way. We use them all the time to tell things about the system, such as subtle variations in pressure and temperature that we can't get from the major components because of the way that trace elements partition into phases as a function of, for instance, what does a mineral lattice look like as temperature and pressure change. So they're useful indicators of things, but they're present in such a small quantity they don't really affect the system. So people like always ask, so what's the concentration of something that counted as a trace constituent? And it's a little bit hard. It depends specifically on the system, and it depends specifically on the chemical. You can have chemicals that even in very, very small quantities really affect the way a system behaves. But in general, I'm talking super generality here, stuff is a trace constituent if it's less than 0.1% or 0.01% in concentration. That's the ballpark, and it's totally a ballpark, but that's kind of what we're talking about. Things that they're present, and as you will see as the semester progresses, we can sometimes look at stuff that's in the ppm, parts per million concentrations, or ppb, parts per billion, no problem. Sometimes we even look at ppt, parts per trillion. So for instance, 1 part per billion means there's one thing, one atom, for instance, of whatever chemical that we're looking at, in a billion other things. That thing is not going to affect the kind of material properties. Whether it's present or not doesn't really matter. But the fact that it's present, in one rock we may have 1 ppb, in another rock we have 10 ppb. That's like, whoa, that tells us a lot about the conditions that rock formed from. And we'll get into those kind of details later. But for now, we're focusing on the major components for these kind of discussions. Okay, so now, blast to the past. I know that thermodynamics may have been painful for you in the past when you learned it. But here's a few terms that I kind of want you to try and remember: enthalpy, entropy, Gibbs-free energy, and chemical equilibrium constants. These things are all related together, and we're going to go through that in a kind of a reviewy way. I just also want to remind you that sometimes you'll see things written as a G or a delta G, for instance, or a delta S or a delta H. Those just mean the change associated with a process, like a chemical reaction. And when I got this little 0 or degree sign next to it, that means it's the standard state, and the standard state, standard temperature and pressure is, 298.15 or 25 Kelvin, with 25 degrees C in 1 atmosphere. It's basically a starting point that we compare stuff to. So thermodynamics is built up with a whole bunch of tables and measurements of these kinds of things that are always given to you at this value, unless otherwise stated. Like sometimes people will say, oh, well, what's the value at 0 degrees C, which is 273.15 Kelvin. What is it at 100 degrees C, which is 373.15. What is it at different pressures? These are things that our scientists makes these calculations all the time. There are equations that say how these things vary with temperature and pressure in a predicted pure ideal materials way. And we're not going to get into all those derivations. The book mentions them. Okay, so you can see them. They're derived using calculus. You integrate across the range of conditions, and we're going to look at the derived equations a little bit just so that we can pull temperature and pressure information out of relationships. But I'm not going to try and derive any of that stuff for you. But just suffice it to say, I think you know this. If you remember learning Le Chatelier's principle, which has to do with when external variables change about a system, how do chemicals rearrange in a chemical equilibrium sense to respond to that system. So for instance, if you have the equation of liquid water evaporating to vapor and you turn up the heat, more liquid is going to go to more vapor. If you turn down the heat, just changing the temperature, you will condense some of the vapor back to water. So that is a way in which the equilibrium constant of the evaporation and precipitation of water is affected by temperature. And pretty much all chemical reactions have some effect on temperature. And we'll see some, pretty interesting ones, like how does the solubility of different minerals change as we go down with depth in the ocean, right? You get down to pretty high pressure at the bottom of the ocean, and the temperature also tends to go down relative to most parts on the planet. And so the solubility of chemicals changes because the equilibrium constant of solubility is a function of temperature and pressure. Okay, so it's like, equation, the Gibbs free energy, right, which is basically all, we'll define what all the little details of Gibbs free energy is, but just to remind you, Gibbs free energy is the total transferable energy in a chemical reaction. And the Gibbs free energy of a reaction, as written at equilibrium, is 0. That's kind of why this thing was developed. Basically telling us that once we reach equilibrium, the total net change in energy as defined by this parameter is not changing anymore, okay? And so that means that the delta G naught, the thing that we can look up the individual Gibbs free energies of formations of reactants and products and add them together to get delta G, is basically a simple function of the equilibrium constant. So the delta G naught of a reaction, the standard state formation delta G's of each chemical in the system, is just minus R, a universal gas constant, T, the temperature in Kelvin, times the natural log of K. Remember, we talked about K last time. It's just the products over the reactants raised to their stoichiometric coefficient. And this is kind of like a gold standard reaction, or excuse me, equation that we use all the time. And we talked last time, if you write out an equilibrium constant and the value is large, larger than 1, then as written, a chemical reaction has products being favored. So you can see, if you kind of remember your relationship of logs, right? And there's a minus sign here. So, a minus sign is basically like exponent. You can bring it over into the exponent. So a large K gives you a large negative delta G. And a small k, meaning a chemical reaction that isn't favored as written, gives you positive delta G. So it's just like when you're looking at equilibrium constants, and you can see values of them and say, oh, that reaction is going to go or not going to go, or it's going to go a lot or a little. You can say the same thing with delta G's. Just remember that they're kind of inverted from each other. So if we're not at chemical equilibrium, right, then this assumption doesn't apply. And so instead, the whole delta G of the reaction is the delta G of formation, the one that's related directly to the equilibrium constant, the thing we can look up in tables, plus universal gas constant, temperature in Kelvin, times the natural log of Q. And remember, Q, the reaction coefficient, we also mentioned it at the end last time, it's written exactly like the equilibrium constant, but instead of having a value of the equilibrium constant, it has a value of what's actually present at any given time in a system, right? So if the mixture of chemicals in a system is really close to chemical equilibrium, then Q won't be all that different from K, and delta G will just be very close to delta G naught. But if the mixture of chemicals is really different than K, so that when we write out Q, we get a really different number, then there's going to be some value that gets added to this that's going to tell us how much impulse there is for chemical reaction. So I still have no guys all. Okay, so there's more. Gibbs free energy, this total chemical reaction energy, which becomes zero at equilibrium, is a function of two main things: enthalpy, abbreviated with letter H, and entropy, abbreviated with the letter S. Okay, and all of these things have standard state values with a little, zeros that are in tables that we can look up. Sometimes we can be lucky enough to find values at other temperatures and pressures too, but we can pretty much always find standard states. And when we're looking at the amount of change in a chemical reaction of total energy, we can express it either as delta G or as how it partitions between enthalpy and entropy. Okay, and we'll look at where both of these things come from in a second, but these are the two main components. We'll see when we get into open systems, okay, systems that can exchange with their surroundings, there's more than this that we have to throw in. Another thing we have to think about is how much stuff is going in and out. So delta G becomes a function of more than just this. And that's something called chemical potential. We'll get to that at the end of it. But in a closed system, these are the kind of two main things that contribute to the energy. Okay, so enthalpy is basically a measure of energy in the form of heat. And you can think of it as some combination of molecular motion or vibration. So sometimes, in chemical bonds, we've got two atoms sticking together, they're vibrating against each other. And they can vibrate in all sorts of different modes. Or think about, like, you're up in the atmosphere and you got a molecule of oxygen and it's zipping around, right? It's got a certain amount of momentum. And that momentum is an expression of its energy. So if you take a bunch of gases in a balloon, for instance, and you heat it up, the gas molecules are going to move more quickly. Okay, that's because the system has absorbed heat, and the way that the heat is expressed is primarily in the motion or the velocities of the molecules. And so that's basically how enthalpy is manifested. So you can sort of imagine scenarios like, how do I change graphite into diamond, or how do I, melt ice into water, or vice versa? Is basically you can absorb or release heat, as the case may be, and reorder the bonds so into a condition where there's more or less molecular vibration, and in response to the changing conditions of temperature on the system. Now, as we'll see in a second, you also need the entropy, the amount of order and disorder, to understand whether a system is going to change in a way that we might predict from just enthalpy arguments, because the two trade off with each other to give the energy. But enthalpy is basically heat. If you can remember that, you've got most of it. So heat is usually written by thermodynamicists with the letter Q, right? And there are various relationships between Q and the amount of work that can be done in a system. And work, which is, when you learn thermodynamics originally, it's usually expressed as changing the volume and pressure in a piston and watching the piston go in or out, which is a certain amount of energy being changed. It can be written as minus P times the change in volume. These two parameters, Q and W, add up to make U, which is internal energy, and U is related to H because H is the internal energy plus the pressure times the volume of the system. And the only reason I give you this stuff, you don't have to memorize this, you don't have to remember, but only to say that heat in a system is some combination of the enthalpy, I should say, some combination of the internal heat and the work that that heat is basically doing in a pressure volume sense. So systems that don't change pressure or volume very much, the heat boils down to a very simple expression, the enthalpy of just the heat. But in systems that are, for instance, I would like to use the example of a magma coming up from the surface, from depth to the surface, where the pressure and the volume are changing a lot. The pressure decreases as we come up and the volume therefore expands. They can use a lot of their heat energy and do work on the surroundings, and that sort of changes the relationship between the various parameters that are expressed here in enthalpy. So, and this is a kind of a long-winded way of saying that in systems that are closed to energy exchange with their surroundings, enthalpy manifests itself differently as we go through a big pressure and temperature change than in systems that can exchange heat with their surroundings. And so you will commonly see calculations that are done that assume, again, this adiabatic condition, which I mentioned before, which says that we can't exchange heat between our system and our surroundings. It makes the calculations way easier. They're not very realistic, but this is a common thing that you see people do just to get some kind of numbers of what we expect, then to compare with what we see in a system, and then we can decide whether or not the system really is closed or whether or not heat has been exchanged. And again, you can think about, for instance, as a magma rises up from the surface, from depth to the surface, it goes really fast and doesn't exchange any chemicals or heat with its surroundings. It's going to arrive just below the volcano in a much more superheated state, and it's going to contain more chemicals that are out of equilibrium with its new condition. For instance, all the volatiles. So it might erupt, a very low viscosity gas-rich magma that might erupt, much differently than if a magma is rising up and slowly exchanging gases and exchanging temperature and kind of cooling when it gets to the surface. That's just kind of one practical example of how these are different and why we use them. Okay, so that's enthalpy. Here's a few more kind of relationships, just to remind you that these things exist, right? So enthalpy change is a function of the heat change and the volume times the pressure change in a system at constant volume. So that if you also keep something what we call isobaric, which means the same pressure, then this whole term goes away and the enthalpy is just the heat in a system. So in isobaric reactions, we can understand the kind of transfer of energy just from the molecular motions, breaking and forming of bonds, changing of phases, etc. And this can also be expressed as a heat capacity times a change in temperature in the system. These are just things that you can look up. You can look up heat capacities for materials. And some of them are high, like water has a very high heat capacity, it can hold a lot of heat over a relatively small amount of temperature. Other materials have low heat capacities, etc. So that's kind of an interesting constant pressure situation. And at constant temperature, enthalpy is a much more complicated expression. It's T times delta S plus V times delta P, and we're not going to worry too much about it, but it basically tells us that it's dependent on the temperature, the change in entropy, and the change in pressure at constant volume. So it's much harder to solve problems using this than it is using that. Okay, so if you want to calculate the change in enthalpy for a chemical reaction, A plus B going to C plus D, we can look up in tables the standard state enthalpy of formation of each chemical in our table, or in our reaction. And then we can just apply the simple expression, which is just that the delta H for a reaction is the heat of formation, the enthalpy of formation for each of the products summed up minus each of the reactions, right? So it's written out here for that chemical reaction. We've got two products, two reactants. So we look up in a table the heat of formation of chemical C and chemical D, and we subtract from it. We add those together, and then we subtract the sum of A plus B enthalpy. And that will give us a value here, okay? And so really, as I say, what enthalpy is kind of telling us is the part of Gibbs free energy that's related to heat that's in chemical bonds, heat that's in molecular ordering, right? Think about the diamond structure or the quartz structure or something like that. And heat associated with molecular motion, just the actual moving around and vibrating of stuff. And so, for instance, the fact that water has hydrogen bonds, which we talked about before, in its liquid state, means that it takes more energy, it absorbs more heat before you can break those bonds and allow a single molecule of water to evaporate off the liquid portion into the gas phase, than we might get for other similar substances that don't have hydrogen bonding. But once it happens, then the heat that's absorbed gets translated into the molecular motion of that, the gas phase molecule. All right, so I have a little bit more stuff here about the kind of bond heat and what this means. So when you look up the heat of formation of a chemical and you find that it is 0, okay, that is a standard convention. Obviously, every material on Earth has enthalpy, it has a value, but it just kind of goes to show you that when we find the form of a chemical, the constituent elements of a chemical that are in its most stable form at STP is given a value of 0. So then all the other heats of formation are actually relative to that. Those tables are relative when you look them up. So we make certain assumptions about things that give us a basis to compare stuff to. And so graphite, which is the common form of pure carbon, not carbon mixed with oxygen or carbon mixed with hydrogen, but just carbon by itself, is graphite at STP. So that gets a delta heat of formation of 0. If we want to write the equation of graphite to diamond, which is something we know happens at high pressure and elevated temperature, we can look up the heat of formation of diamond and find a value in the table, right? And it's minus 453 calories per mole or minus 1.87 kilojoules per mole. When I use chemistry, I learned it all in calories, which is not a non-SI unit that people tend not to use anymore. They tend to use joules, but somehow my mind always goes back to calories or kilocalories. So there's a conversion. If you're looking up numbers and you're adding them together, you just want to make sure you're using the same units, right? Whatever it is that you prefer. There are other units that you can use as well, other systems. But if we look up the heat of formation of diamond and we find this value, right? That's telling us that to make graphite into diamond, we have to absorb a bunch of heat from the surroundings, right? That's part of what has to happen.
I have a question. Do we do that? Like, I mean, I don't know. Because if you can turn like graphite into diamond using like heat, do we do that like artificially?
Yeah, the part of we make micro diamonds. It turns out that even though it seems like a simple recipe, it's really slow.
Yeah.
Right.
Oh,
And so on human timescales, it's really hard to do this. If we had millions to tens of millions of years to wait, we could totally do this.
Oh, I see.
But because it's happening in a lab, they can make really tiny little things.
Yeah. Oh, okay.
Okay, so here's just like the next level up with the enthalpy, which is basically to remind you that sometimes the quickest way to calculate the enthalpy of a reaction, and this is also true with entropy and it's also true with Gibbs free energy, is to combine various chemical reactions that we find in a table that tell us the relative variations and then mathematically combine them to come up with the answer. So it's a lot easier, rather than to try and do this chemical reaction in a lab and see how much energy it takes to make diamond out of graphite. Another thing we can do is just take some graphite and take some diamond and make a powder and burn them with oxygen, make CO2, and measure how much heat change happened, right? And then by combining these two things mathematically, right? So if we just reverse the order of this reaction, write it in the opposite sense, and then add them together, we'll see that we have oxygen and CO2 are going to drop out in an algebraic way, and it reduces back to this equation, right? But in the lab, this is something that's easier to measure, and you can see how much energy, is released when we do that, and you can add those two things together and come back up with the same exact number that we just had. So this is a common way of calculating things, and it will be true when we talk about redox as well. Sometimes the chemical reaction that you are looking to solve for isn't the thing that's in a table. You'll find some other thing, and you add those things together in a way that algebraically cancels out the things that you don't want to give you the result that you see. I just want to make sure, does everyone get how we can algebraically add these two equations? Right, with chemical equilibrium, I always think about two arrows, it's just like an equal sign. And then you just apply your rules of algebra. Flip this one around and then add the two things together, and you'll see that the oxygens sit on opposite sides of the equation, so they cancel each other out, and the CO2s as well. And then you just have graphite going together. And in that case, we just add the enthalpies. Okay, so here's the other kind of enthalpy besides the bond energy, is the phase change energy. Okay, and so there's a couple of abbreviations that are used all the time. One of them is called the heat of fusion, right? So abbreviated is FUS, delta H of fusion. That term is applied to when we go from a solid to a liquid, or when we go from a liquid to a solid. Even though in one case we're fusing is melting and whatever, what's the opposite of melting? Freezing, but they're both given the same terminology. Another one is delta H VAP, or for vaporization. Whether or not something is going from the liquid to the gas phase or condensing back, it's still explained with the same terminology. And if you just think about it, it is the amount of energy in the form of heat that needs to be added to a system to change how it is structured, right? To go from a solid to a liquid, for instance, we need to release all the bonds holding together a solid and allow those chemicals to float freely. If it's graphite and diamond, like the example on the last page, is basically rearranging the bonds to be from sp2 hybridization to sp3. It's a complete and total reorganization of the structure. So there's a lot of heat involved in phase changes. But we don't always have phase changes, right? We don't always have reactions where we're reordering our substances. But when we do, most of the energy that is added or subtracted to a system goes into changing the relative proportion of phases, like melting water or freezing water at the surface of a glacier, for instance. So that's a really important kind of enthalpy, which is totally different than this kind of enthalpy that's associated with the forming and breaking of bonds between different chemicals in the system. There's a third kind of energy, which is the kinetic energy heat, which is what happens when we add heat to a system at places where we don't expect a phase change. Like, let's say we're heating up some water between 40 degrees C and 50 degrees C, right? We've heated it up. We're not expecting to get a huge amount of vaporization. Most of the heat that we're adding is going into making the molecules of water just move around a little bit more quickly in the pot of water. Okay, and that's where this term, the change in enthalpy coming from the heat capacity times the change in temperature, that's where that equation I showed you before is really useful. So depending on what chemicals we have present, if we are at the place where we expect a lot of phase change, like 0 degrees C for freezing of water or melting of water, then when we add heat, most of it's going to go into this. If we're away from that place, most of the heat is going to go into this. And, you know, plus minus in both cases, the amount of chemical reordering that might be happening. All right, so now we got entropy. People think about entropy in a lot of different ways. It's really the number of degrees of freedom we have in the system. And nature tends to prefer higher amounts of degrees of freedom. Degrees of freedom are sometimes called, you know, disordered relative. So high degrees of freedom is highly disordered. Low degrees of freedom is ordered. And so some people basically, you know, think of entropy as a measure of order. It's a way of thinking about it. If that works for you, that's cool. But basically, it's how many things we need to know about a system to be able to define it. And it turns out that nature prefers to go into a situation where that number is high, which doesn't work very well for us as scientists, right? We're like trying to like, hey man, we want to understand what's going on here. Wouldn't it be great if nature were working towards us and moving towards systems with less disorder or less degrees of freedom? But that just isn't how it works. So in a way, you can look at a system and say, as it's absorbing heat and rearranging chemicals and doing its thing, and obviously there are delta H reasons that we just talked about that will help determine the proportion of stuff that's present when we start, you know, cranking on a system with heat and pressure. They're counterbalanced by the arguments here with entropy. So for instance, if one molecule is breaking apart into a whole bunch of different chemical constituents, that takes us from a low entropy to a high entropy state. And even if from a delta H reason, that reaction isn't favored, the reaction may still happen because it is favored from an entropy reason. So other than that, you know, there's some other relationships, such as the entropy is basically the heat of a chemical reaction divided by the temperature. Sometimes useful to know also the change in entropy of a reaction is the heat capacity times the change in temperature. And we can look up standard state entropies in a table, just like we can for enthalpies. And they are all referenced relative to the standard state of entropy of hydrogen ions being 0. So we build up a table with values in them that are only calculable because we're doing them relative to hydrogen ions being 0 at STP. And other than that, the way we calculated delta S for reaction, and just by the way, I'm not going to have, I don't think, have you do any of these kinds of calculations, so you don't have to worry about it too much. But you basically would just sum up the delta S of formation that you pull out of the table for all the products and all the reactants, you know, so add the products, add the reactants, subtract the reactants off the product, and that gives you a delta S of a reaction. And you can use your delta S and your delta H to calculate a delta G. Okay. We can also look up Gibbs free energies of materials and calculate them by the same principle, right? And if you, this is just a reminder of what I showed you, you know, a few slides back, that the Gibbs free energy of a reaction is the Gibbs free energy naught plus RT times the natural log of the reacting coefficient. And at chemical equilibrium, this goes to 0, Q turns into K, and we get left with this simple expression. And so G, which is basically just H plus P delta S, enthalpy plus temperature times entropy, is a reflection of the total heat and disorder in a system, and it is directly translatable into an equilibrium constant. So, and this is basically just like the formal way of writing out, you know, the relationship between Gibbs free energy, enthalpy, and entropy. So, there are other useful generalizations about these things, which are all derived in the reading using, as I say, differential calculus. But one of the things that we find is that the change in Gibbs free energy is basically a volume times a pressure change minus a entropy times a temperature change. And for some, chemical situations and environments, this ends up being the major form of energy that's determining the kind of what could happen with the chemical reaction. And others, it's that. And still others, it's somewhere in between. But for instance, these things can be used to look at how these parameters, changing in pressure or changing in temperature, which are both things that happen that we deal with a lot in the earth sciences, are how are they manifested into changes in Gibbs free energy and therefore into the equilibrium assemblage of chemicals that we expect for any system of any components, right? Because remember, this is just basically minus RT log K. So, and for instance, just going back to the water phase diagram, right? So you can see here the slope between liquid water and solid ice, and it's actually slightly negative. It's an kind of an unusual situation. Most chemicals as a pure phase have a positive slope here, and that slope comes from something called the Clapeyron equation. So sometimes people say, oh, water's got a negative Clapeyron slope, which is basically a reflection of how it responds to temperature and pressure as we start to change those things. And it turns out that, as we squeeze on these things, the temperature of freezing actually goes down as we go up in pressure. It's a little bit hard to see, but it's a slightly negative slope. Whereas for most chemicals, as you turn up the pressure, the temperature of freezing goes up. And that's just one of the kind of another unusual characteristics of water. But this is kind of where it comes from.
Does that happen to water just bending as it freezes?
I'm not exactly sure what property of water makes it do that, to be honest. I don't know. It's because the problem is that if you keep it in a system that that is closed, it can't actually expand, right? Because the volume is fixed. So if you allow volume to change, then maybe it would do that. But if you keep volume fixed, it has something to do with the ordering of the molecule itself, the water like ice structure, and how as you put pressure on it, it changes the amount of internal energy that's stored in all the bonds that are holding it together in a way that it's easier to make it squeeze together. As pressure goes up, it takes less temperature. Yeah, it's a weird property of water. Okay, so here's like a free energy calculation. This is for the mineral malachite. It's this characteristic turquoise, it's copper hydroxycarbonate. And this is something that precipitates from water. It's the same kind of material, basically, that you see oxidizing copper piping and copper flashing that you see like along roof lines and so forth. Basically, aqueous copper ions, carbonate, which obviously comes from the atmosphere, CO2 dissolving in water and dissociating, as we talked about last time, plus some OH ions, hydroxyl ions. Water always contains some H pluses and some OH minuses. So this reaction consumes some of those that makes this mineral. It's a salt, right? It's something that can dissolve back into water. And so the first thing that in this example I want to show you is how I balance this equation, right? So this is material balance. I had to put 2 of these here and 2 of these here with 1 of these. So, right, copper 2 plus, OH 2 carbonate, just looking at the thing, a molecule. We'll talk about oxidation states later, but remember last time I mentioned that one of the classes of chemical reactions is a redox reaction where something changes its oxidation state. This one is not a redox reaction. Carbonate anions, we talked about before, have a 2- charge on them. OH ions are 1-, OH minuses. And so we got 2- charges here, and we've got 2- charges here for a total of 4- charges. We got 2 coppers, right? So each copper, and this is a non-charged molecule. So if we got 2 coppers balancing 4 minus charges, it means each one of these have to be a +2 charge. Right, +2 and +2 is +4, which balances the -4. And over here it's also +2. So this copper hasn't changed. We do have lots of reactions that we're going to talk about during the semester where even written out like this, this chemical will change its oxidation state as it forms a solid, but this isn't one of those examples. So basically the material is balanced, the charges are balanced, another thing you could check, right? We've got 2 minuses and 2 more minuses makes 4 minuses, and we've got 2 times 2 plus, we've got 4 plus and 4 minus, so that all balances out 2. Okay, and so I just want to remind you that when you're balancing chemical equations, please make sure that you balance the material and the charges. And it's usually in trying to balance the charges that you can figure out whether or not something has changed oxidation state. We'll get to that in a coming in a lot more. So for instance, if we wanted to look at the Gibbs free energy of formation of this stuff, we can go into a table, right, and pick some numbers out and basically calculate a delta G of reaction, right? So we can look up the value for malachite, we can look up the value for copper ions, carbonate anions, and hydroxyl anions. And the way they're going into this equation is that these things are being multiplied by their stoichiometric coefficient, right? So there's 2 hydroxyls, so we're multiplying it by 2, right? And there's 2 copper ions, so we're multiplying it by 2. And we just add this stuff together, right? This is the sum of the products minus the sum of the reactants. And we do all that stuff, we come up with a value of about 10 to the 34 or 33.7. So this is a really high equilibrium constant. It tells us that this chemical reaction is pretty favorable, right? If we got some mixture of copper and carbonate and hydroxide, it's probably going to make this stuff. Because it's got a really high equilibrium constant. At chemical equilibrium, we have 10 to the 34 times more of this stuff than this stuff, right? If we think about our equilibrium expression. So that's a lot. Okay, so let's see where we are in time. All right, about 15 minutes. So I'm going to start on this topic and we're going to talk about it a lot more next time. Chemical mixtures are really common in nature. And how things behave as a function of being in a mixture is an important aspect of how we describe systems and how we expect systems or materials that we find on the surface or the interior of the earth, how they vary as a function of changing conditions. And this is basically, if you think about mixtures as basically a combination of multiple pure materials, right? So we've already talked about what happens to pure materials when we move them through gradients in pressure and temperature. They absorb heat, they give off heat, they reorder, they do those kinds of things. But when we look at mixtures of materials that are intimately mingled with each other, then we can think about them in 2 ways. One way is how much change do the pure materials make, and how much additional change do we get because they're together as a mixture, right? And so that being together as a mixture gives us, you know, an additional term or an additional aspect of the system that we sometimes want to pull out and quantify. And we do that using something called partial molar values, which is a fancy way of saying that in a material that is a mixture of various stuff, we want to understand how much change is happening in that system as a function of the fraction of each chemical that's there in molar quantities, right? So we don't use weight quantities, we don't use, you know, any other measures of concentration, we use molar concentrations. That's because chemical reactions are stoichiometrically written in terms of moles. And so if we look at the amount of energy or the amount of enthalpy or entropy or Gibbs free energy or what have you in a system that is related to just one part of it, we determine that with something called a partial molar value. Okay? And the partial molar value of a phase, okay, right? So pH is just an abbreviation of phase here. A is whatever phase we have, so the chemical. Sodium chloride ions in water, sodium ions, might be the thing that A is solving for, and a phase is equal to ions. It is going to be the change in that value divided by the change in the number of atoms, or it's actually moles, I should say, and in moles in that system, whatever's happening in that system. Maybe it's just exchanging with its surroundings, maybe it's undergoing chemical reactions, whatever it is. But it's basically just boiling down the change in a parameter, okay, as a function of how much of the moles of that parameter are changing. So this is really useful in open systems too, where stuff goes in and out, right? If N changes, then we can say, oh, well, how much is the, Gibbs free energy going to change because we're letting, CO2 bleed out of our magma as it rises up to the surface. And therefore, how is that going to change the overall Gibbs free energy of the system? So if you divide up your system into each of the phases in proportion by the number of moles that are present, then whatever value we're looking at, whether it's enthalpy or entropy or Gibbs free energy or what have you, the sum, the overall entropy, enthalpy, whatever, is the sum of all the partial molar values, right? So basically, it's just a way of dividing up the individuals as a function of total N. So I just have a couple of examples of how that might be useful. So let's say we wanted to know the partial molar volume, or how much space is taken up by two end members in a mixture: calcite, which is calcium carbonate, dolomite, which is calcium magnesium carbonate. Basically, all it is taking the calcite structure and sticking in some magnesium. And in pure dolomite, which has a range of compositions, we're talking about something like 10%, maybe 15% magnesium stuffed in there. When we look at the chart, we can see magnesium is smaller than calcium. So it's going to disrupt that lattice a little bit, right? And so this happens. It happens a fair amount in certain settings. In other settings, it doesn't happen. It depends on a variety of parameters, but especially the amount of magnesium that's available. And so we can calculate that using partial molar values. Another example is that phosphorite phthalate example that we talked about before. So sometimes people will write out olivine with 80% of the magnesium end member and 20% of the iron end member, which is physically depicted as that. They'll abbreviate it as FO80, right? That just means it's got 80% of this magnesium silicate proportion, and therefore usually 20% of the other. And again, these things take up less space. The size of the ions are different. Magnesium ions are a lot bigger than iron ions, so that's going to have an effect on the structure. And we could calculate using these partial molar values, in this case for volume, the relative proportion of effect on that molecule. Okay, I'm not going to go through the calculation, but there's things that you can look up. You can look up values and you can say, oh, how much will the partial molar value of, whatever, a calcium carbonate deposit change as a function of doubling the magnesium concentration or something like that. But where partial molar values are even more important are in this calculation, this thing called chemical potential, which is the thing I mentioned at the beginning, is maybe the one thing of all the stuff that I'm talking about that you haven't heard of before. Chemical potential is a partial molar Gibbs free energy. So what it is like if we look at the Gibbs free energy of all our chemicals in a system and we parse it out into how much of the Gibbs free energy is related to this chemical and that chemical and that chemical. And we give the proportion as by the moles, how many moles of each chemical is present. Then just like for other things, basically the sum of all of the partial molar Gibbs free energies added together tells us the total Gibbs free energy. But it turns out that this partial molar Gibbs free energy is given a special term name called chemical potential, because in cases where the chemicals are not fixed in an environment, they can move in and out. For instance, we get a change in the Gibbs free energy that we would sometimes like to relate to the specific chemicals that come and go. So that's why we define this as a special term. So the sum of chemical potentials, which is usually written with this Greek letter mu, okay, right? Mu is basically, if we add up the mu times the change in moles of that particular chemical constituent I, and we add sum up all of those things together, we come back to just the overall Gibbs free energy of a system. So the mu of one chemical in a system, chemical A, times the change in the number of moles of A is the change in Gibbs free energy. I'm missing the little A here. That's related just to A. Okay. And so another way of thinking about this is the chemical potential of A is the change in Gibbs free energy divided by the change in moles of A. And like I say, this becomes useful for these two things. If we're describing an open system where the number of moles of our stuff is not fixed, stuff's coming and going, we can ask mathematical questions like, all right, how much does this system change if, as the magma is rising up from depth to the surface, we allow carbon dioxide to exit and we don't allow carbon dioxide to exit, or we allow water to exit or we don't allow water to exit, or other things, we allow olivine crystals to form and settle out or not. And so that's one way the chemical potential is useful. The other way is when we study mixtures, right? And this is something we're going to talk about a lot next time. Mixtures meaning things like the olivine solid solution, or the feldspar solid solution, or metamorphic minerals that form as a function of pressure and temperature in a certain setting, and then maybe those rocks get moved to a different pressure temperature space and the minerals start to rearrange and so forth. And we can look at how mixtures change as a function of changing pressure and temperature, and whether or not they exchange materials with their surroundings or just rearrange internally within them. There is a chemical potential, which is the part of the Gibbs free energy that's related to each component within the system. And this is oftentimes a useful way of looking at stuff. There's also useful to remember that just like for Gibbs free energy knot, which doesn't change at chemical equilibrium, that in a closed system where we're not allowing any exchange with the boundaries, and when it is at chemical equilibrium, if we sum up all the individual chemical potentials of all the materials in there, times the change in number of moles, it has to be 0, which is just a fancy way of saying delta G equals 0, which we know delta G not equals 0 at a chemical equilibrium. And if you just go back to the definition, right, it's just mu times A is delta G. So as I say, this is kind of a slightly different way of thinking about stuff. And we can use it, for instance, in cases where we have minerals that are solid solutions, and they're almost never just the simple end member like phosphorite, phthalate. There's other end members in there too. There's trace constituents. It's useful for looking at mixtures of gases. It's useful for looking at mixtures of liquids. It's useful for looking at the solubility of things in water. So we'll apply chemical potential in a couple of cases, and especially for the trace constituents that I mentioned at the beginning of the class, we have a whole, or at the beginning of the class today, we have a whole theory of what we call trace element partitioning, which is sort of how does the chemical potential of each little chemical in the periodic chart measure up against the chemical potential of all the other things to give us all of the small amounts of substitution that we have of all the chemicals present into whatever phases we have present in our system. So it could be, for instance, the minerals in our igneous rock, and we want to know how much strontium and how much barium is in our plagioclase, and what is that telling us about the conditions that it formed at, or what is it telling us about the material it formed from? And this is where kind of chemical potential becomes the most useful. I think that's, I have one more, let's see, I'm trying to remember what this is. Oh, it's just like another way of explaining, basically changes due to sort of one constituent of a phase. So for instance, if we have argon, which is the third most common gas in our atmosphere, and it dissolves in the oceans, at chemical equilibrium, if we go back to Henry's law, which tells us that the amount of argon that dissolves in the water and the amount that's in the atmosphere are related by equilibrium constant, so that the ratio of their Gibbs free energies is constant K. We express the Gibbs free energies as mu's times delta n's. We can look at how much change energetically do we see in seawater due to the coming and going of argon. It ends up not being very much. At chemical equilibrium, we know that this value has to be zero, the net has to be zero, but if we know some of these things, we can get the other ones and we can figure out the relative effect. Like that, no, oh, sorry. This is the basis of what we're going to mostly talk about next time, but this is the chemical substitution that I was just talking about. Like for instance, in this case, this is the solubility of rubidium in the plagioclase instead of barium and strontium. So rubidium is here, +1 ion. And let's say we've got two minerals in our rock. We got some plagioclase, we got some planet pyroxene. We want to understand, well, how does rubidium decide if it's going to go into plag or if it's going to go into planet pyroxene, and how much in both plagioclase, planet pyroxene, CPX, those are the abbreviations. We can write out a simple expression that basically tells us how the partial molar value concentrations as a function of chemical potential are going to vary as a function of the change in moles between them. Write out the equilibrium situation, which is that as plagioclase and CPX are sitting together at equilibrium and exchanging rubidium between them, the total net Gibbs free energy is zero. And so we can basically come up with a simplified expression that says that the chemical potential of rubidium in plagioclase and rubidium in planet pyroxene is equal to each other at chemical equilibrium, which allows us to calculate something called the distribution coefficient. Distribution coefficient is basically the ratio of these two things divided by their change in number of moles. And that is something that I will talk about next time. And as I say, this is like a slightly different way of thinking about thermodynamics than maybe you're used to. And as you can imagine, in a situation where we've got plagioclase and planet pyroxene sitting next to each other in a magma or somewhere else, they don't just have rubidium in them, they got a whole bunch of other chemical elements in them. So we can't look at the chemical potential of rubidium without knowing the chemical potential of strontium and barium and cesium and a whole bunch of other chemical elements. So it becomes more complicated than we would like. We can't necessarily just apply pure thermodynamics, but we can apply the kind of mathematical underpinnings of thermodynamics to these non-ideal situations and figure out whether or not we're close to equilibrium or far from equilibrium, and or whether or not the phases are behaving really non-ideally, which will be one of our main topics next time. So far, everything we've talked about here is for ideal materials, things that don't interact with each other in ways that deviate from ideality. But as we'll see, in natural systems, a lot of non-ideals. Okay. So again, I know this is a bit of a whirlwind, and are there questions?